Vectors are general terms. We just covered ordered pairs, right? And I'm about to explain position vectors and displacement vectors. Okay, those two things I explain it here. And they're saying, at this point, vectors in the plane. This position vectors is a coordinate. In xy plane, for example, if you know those. So position vector can be explained like this. Y coordinate here. This xy coordinate plane, right? So if you have a point in here, you can write it as 3, 3. That seems like the same notation we use the ordered pair, right? So that's a point in xy plane. That's a position. So how are we going to turn this one a vector? You can just accept it as a geometric information. It is a vector. But they like to use arrows, right? From here is arrows. Position, when we say position vector, is a position relative to origin. That's what we're saying. But if you want to describe a position relative to some other point where you are standing in here, for example, then it's position vector relative to some point. You have to specify like that. If we use position vector, it's going to be position vector from here to there. So we use arrow from here to there like that. That's a position vector. So when you say position vector, this initial point, I'm going to call it the point of application. The initial point is always at 0, right? That's what position vector is. Okay? So these arrows joining all these initial point at this origin is called position vectors. It is very, very easy to see what vector is equal to another vectors. In this vector and that vector is different, right? And that vector is different. It's a kind of different arrow starting from there because all the points are different. All right? Do you see the 0 vector? Starting here and ending at the 0, 0. So that will be just one point collapsed vector, right? That's a position vector. So what is a displacement vector? Is that if you have xy plane, I have one point here, you were there, and 2 seconds later that you were here, right? And this vector describes how you moved, not from where to where, but it's just indicating you moved from here to there. Because of this point of application, you know where it starts and where it ended. It doesn't mean that it actually travels straight line. It may be in 2 seconds you moved like that, you end up at here. But displacement vector is the initial position and the observed position after 2 seconds, for example, and you write it as a straight line. You were here one moment, next moment you were here, observed to be here, and this is a displacement vector. Strange thing about displacement vector, this displacement vector only records how you moved. For example, you moved 3 units to the right and 1 unit above. That's the only thing this vector records. This vector is going to be denoted like 3, 1. Crazy. This vector, displacement vector, is denoted like this. When I say I have a displacement vector 3, 1, you don't know where it started and where it ended. You only know how much it moved. That is called a displacement vector. Ignores the point of application. Right? But in the context, it exists with this one initial point and terminal point. Alright? So that was there. How about this one? I go 3 units here and 1 unit above. And I go write it like this. This is also displacement vector, right? Is these 2 vectors are the same? Yes, because displacement vector only records how much you moved around. So this is supposed to be perfectly parallel. Sorry about that. This vector is called 3, 1. How about this vector? Also 3, 1. That's a displacement vector. Right? So that's what they're talking about here. You started from here, going there, or if you started from somewhere else and going there, their displacement amount is the same. Therefore, we recognize these 2 vectors, the same vector. Apple hovering here, apple hovering over there is the same apple. One way to look at it. Okay? So they're also explaining like this. If you go from P to Q, and this displacement amount in x coordinate and displacement amount of y coordinate, that's what we care about. Not these complete context where it's starting from and where it's ending. Nothing like that. So they're explaining this vector addition and scalar multiplication. So we're looking at the displacement vector. How are we going to add two displacement vectors? I think this is very natural. So for example, so let's focus on displacement vector for now. Y-axis, x-axis there. So if you start from here and go this displacement vector, we're going to call that one vector v. Right? Is that okay? So v doesn't care about this one, how much you go to the right and up. That's what displacement vector is. And next moment you go from here to there. That's a vector w. That records how much you go to the right, how much you go below. So it's going to be negative y component. And what is the total displacement? It's going to be like this one in here, right? And that's going to be the definition of a v plus w if it is displacement vector. Is that okay? All right. Yes? Right, from here it's kind of going below, right? So you can write this displacement vector like this, x2 maybe y2 like that. This y2, we expect, if it is an accurate picture, we expect y to be a negative number, correct? Because you're going down. x2, still slightly to the left, so x2 is going to be a positive number, right? How about this one, v1? x1 being positive number, y1 being positive number, right? Now we have new displacement vector going from here to there, right? So that must have x component and y component. This is a geometric definition. Then you wonder what is the answer to v plus w, right? What is the answer? It is actually x1 plus x2, y1 plus y2. That's the short answer, and it's not that obvious. You have to think about it. And from here, pay attention to what happened to the x. You go x1 amount here, right? And go to the x1 amount. Think about what happened to the y coordinate. You go y1 and go down by y2, right? But y2 already has negative in it. So all you have to do is just add, not subtract. y2 is a negative number, right? So that's how you add displacement vectors. The meaning is quite natural, right? How about position vector? If I have two position vectors, the meaning of adding two position vectors is kind of weird. If I have one position vector here, let's say that's v, position vector, I have another position vector there, w, adding these two position vectors not as natural as going in displacement vector. So why don't I change this one to force vector, and then it's really natural. Suppose there is a billiard ball right at that center, and there is a blue-red ball is coming toward that direction, and another a red ball is coming to that direction. It's collide with that third one, creating impact force. And this one is representing how this is the direction and how much the force is applied. The length is like how hard the force is, and this one is going that direction. And this length is representing the amount of force, magnitude of force applied there. So if it collides at that moment, what's going to happen to how much of the force is actually totaled up? And that's a natural way of interpreting this, adding this two vector v and to the w rather than position vector. All right? Do you know the answer? Can you sketch the picture? They start from here and draw this line that's parallel to the other side v, and starting from here, that is parallel to the other side, and you go like this. And physicists claim that the force that exerted together, and total force, is actually this amount and is that direction. That's a physics assertion. How we mathematically justified, you have to turn that into using the Newton's law of motion to the acceleration, which is more mathematical quantity, and then you can analyze it. But there's still physical intuition there, the law of motion. Forces directly turn into an acceleration. That's a physics. From there, we can mathematically justify this happens. All right, what's the answer here? If it is x1, y1, if this is x2, y2, and what is this position vector? Same thing. v1, not v1, x1 plus x2, that's position vector, and y1 plus y2. That vector is position vector is just that. And if you analyze these two things, kind of this parallel law here, parallelogram, you can see that's exactly the same thing, right? But without much further explanation, we accept that this is true. Is that okay? Force vector or position vector and how the displacement vector works is pretty much the same. How it, the algebra to this ordered pair interpretation is exactly the same. That's vector addition. If you have two displacement vector and you know how to add those, you know how to sketch the picture. If it is two force vectors, makes sense. And if it's two position vectors, there's no meaning to it, but we'll formally define. If you add two position vector, that's the same as that force vector. Simply add those first entries and second entries. Good? Scalar multiplication. What is the meaning of a scalar multiplication? If you have a vector in here, if you have a vector there, v, x and y, what is 3 times v? That's the scalar multiplication. We define it algebraically, right? Meaning of it is actually stretching this one further to 3 times, right? So if it is a force vector, the meaning of 3 times v will be increasing the magnitude of force 3 times, but the direction is the same, right? You're still applying the same force to the same direction, but 3 times the magnitude. And you probably know the meaning of negative 3v. If this is original vector v here, negative 3v will be opposite direction with the 3 times the magnitude. But the way it works in algebraically to the ordered paired interpretation, that's exactly the same across all different interpretation of vectors. All the same. So here is a negative 3x1, negative 3y1. Isn't that right? That's a scalar multiplication right there. Okay? Algebraic definition is all the same, cold blood, simple. But this interpretation of different vector in different situation, addition and scalar multiplication, is worth thinking about it. I gave you the force vector. Displacement vector is a little bit weird with the scalar multiplication, but you just follow the algebraic definition, and that's the definition of addition and scalar multiplication of vectors. I have 1 minute left.